Hello everyone, welcome to part 3 of the space topic. Having had a look at satellites and how we travel through space, now I want to have a look at how we launch our spacecraft into orbit. This entire section is just really having a look and focusing in on Newton's laws and why, well, in particular, Newton's second law, which is the one that you remember as F equals ma, will help us here when determining why a spacecraft launches the way it does. Because a spacecraft, when it launches, it does not launch immediately at maximum speed. It starts off very, very slow and picks up speed almost the entire time it's going into space. And the 3 reasons here are all really important. So the first thing is there's less air as you move up and away from the Earth. Basically, the atmosphere becomes less dense, there's less particles there, so the friction gets less. And if the rocket is still producing the same downward thrust, the same force to push it upwards in the air, and it's meeting less resistance, it's going to accelerate. It's going to get faster. The next thing is that as we move away from the surface of a planet, the gravitational field strength gets less. And because it gets less, that means the rocket quite literally weighs less the further it moves away from the surface of the Earth. So again, as it moves higher, not only is there less air particles for it to be resisted by, it literally weighs less. So the same force is going to accelerate it faster. And then finally, as it goes into space, as it continues to travel through the atmosphere, it's using up the fuel, which means there's less and less mass inside the rocket because the fuel mass is slowly disappearing. And that also means that the spacecraft's increasing. So all 3 of these lead to the spacecraft increasing speed. Now, even with all of these combined, it's not quite enough to get us into space. Now, this is something that's a wee bit beyond what you need to know for National 5, but I think it's interesting. Basically, once the fuel in the main rocket boosters is used up, well, there's just a big heavy tank there that's not doing anything. The earliest people looking at this, actually a man called Tsiolkovsky, who was a Russian maths teacher back in the 1800s, figured this out. Basically, they dump the tank, they drop it. So anytime you see a movie of a rocket going into space, you almost always see a shot where the camera looks back and you see these big tanks coming off. That's because all the fuel in them has been used up. But this actually is using Newton's third law to help us. Because for every action, there's an equal and opposite reaction. When A exerts a force on B, B exerts an equal and opposite force on A. Whichever way around you've been taught it, the idea is that when it drops this tank, it gives the rocket another boost up. And that extra boost from dropping that tank is a requirement to get a craft into space. Now, once we're in space, we have more of an issue because, well, space is big. Very, very, very big. The smallest distance, which is really worth thinking of, is the distance from the Moon to the Earth. So I'll give you a moment to think about that distance. Distance from the Moon to the Earth is 400,000 kilometres. 400,000 kilometres. That's enormous. Now, okay, the Moon's 400,000 kilometres away, but very rarely are we dealing with the Moon when we're looking into space. Frankly, we're usually dealing with stuff much further away than even the Sun. Now, our Sun is about 150 million kilometres from the Earth. So, yeah, that's quite a long way. And even then, when we're dealing with space and astronomy, we're very rarely dealing with something as close to our Sun. So if we were to have a look at what the closest star to us is, a star called Alpha Proxima, it is much, much further away. Okay, it is 40 trillion 140 billion kilometers from Earth. That's a phenomenally huge number, and that is the closest star to us other than our Sun. So we need a new unit. We need a new way to measure distance through space. And the way that we do that is by using something called the light year. Now, the light year is, first of all, it is a distance. It's how far light can travel in 1 year. And light is ludicrously fast. It is the fastest thing in the universe. Light travels 300 million meters in 1 second. Remember, that's so fast that in 1 second, light could travel around the entire planet Earth 7 times, if it could bend around corners. But if we were to convert that back to thinking about the moon is only 1 1/3 seconds away from the Earth. The Sun is 8 minutes away, and Proxima Centauri is 4.1 light years away. What I want to do though is show you how we do this conversion. Okay, this is the one bit of maths that I'm including in the videos because I think it's key that you know how to do this. So we need to make a light year. So 1 minute is 60 seconds, an hour is 60 minutes, a day is 24 hours, a year is 365.25. You need to remember that 0.25. 365.2 days. 0.25 days. So the number of seconds in 1 year is all of that multiplied together, 60 times 60 times 24 times 365.25, which comes out as 31,557,600 seconds in a year. And to get 1 light year, well, 1 light year is the speed of light times the number of seconds in a year. So that means a light year is 3 times 10 to the 8 times 31,557,600 seconds, and that gives us 9.47 times 10 to the 15 meters, which is that when it's written out. And again, that is a ludicrously big number. Okay, so here is an example that we're going to use to see how light year works. So our solar system is in a galaxy called the Milky Way. And the distance from the Earth, the centre of the Milky Way, is 2.84 times 10 to the 20 meters. And we're being asked to find out how many light years the Earth is from the centre of our galaxy. So what we've got to do is we've got to start with our distance, which is 2.84 times 10 to the 20 meters. And we know that 1 light year is 9.47 times 10 to the 15 meters. So if we divide the 2.84 times 10 to the 20 by 9.47 times 10 to the 15, that gives us 29,989.44034 light years. Except, hopefully you all know that's not the correct answer because there's way, way, way too many significant figures there. It's 30,000 light years. That's how far the Earth is from the centre of our galaxy. So just to give you, again, a sense of scale, our galaxy is about 100 up to 110,000 light years from one side to the other. So we're about a third of the way out towards one edge. So second to last, we're going to have a look at the origins of the universe, the Big Bang. The idea is that, well, we think the universe started about 13.8 billion years ago, where all the matter and all the energy was all in one point, and it expanded outward. And that's the key. It expanded. It did not explode. The Big Bang conjures up all kinds of images, but the big one to get is the universe did not explode. It expanded. The idea is it expanded very, very quickly. And this process called inflation, basically the universe just kind of swelled up so fast that not quite everything could keep up with it. And then it slowed down. And the universe cooled down from being super hot to cooling down to a temperature where, atoms could start to form. And groups of atoms could start to form. heavier atoms could start to form. Over time, you started to get clouds of dust, which eventually formed into stars, which eventually grouped together into galaxies. And this has slowly been happening over the last 13.8 billion years. So this is our whole description of it. Basically, 13.8 billion years ago, it's expanded out, and everything to do with our physics began back there. We've no idea what happened before then. The actual final section of this topic is examining how we learn about space, because it's kind of tricky. We don't bring stuff back to Earth. We don't get to bring a chunk of a star back to look at it. We might get some rock or metal that collides with our planet and we can examine, but really we need to use light. We need to examine space using light. So we're using the electromagnetic spectrum. Visible light, but all the other colours as well. So again, you need to remember all the different forms of the electromagnetic spectrum. You need to remember about your gamma rays, your X-rays, your ultraviolet, your visible, infrared, microwaves, radio waves. You need to know all of them. You need to know about which way the increase in frequency, which way the increase in wavelength. You should know that the increase in energy in the same direction that the increase in frequency. So gamma rays are the high energy ones, radio waves are the low energy ones. That isn't what we're here to talk about. We're here to talk about how we can use these different types of light to learn about space. So, I have a few slides here which explain what happens. The big one, or one of the big ones, is ultraviolet. So this is our sun, as seen with ultraviolet light from Earth. And the reason I'm adding in from Earth here is because of that visible light image. There's something wrong with that visible light image if it were taken from space. And that's that when seen from space, our sun is white. It's not yellow, it's not orange, our sun's white. It gives out every single colour of light. It's just that when we're on Earth, our blue atmosphere hides some of the light from us, which makes it look a bit yellowy-orange. Ultraviolet light, though, that is what we end up seeing, and it's great. We end up seeing lots of detail in it. We end up seeing regions where there's lots of different magnetic flux happening, changes in the magnetic field around the sun. And that's what those little dark spots are seen in the visible light image, and you'll notice that the places that show up white in the ultraviolet image are in the same places that the black spots are in the visible image. So the different types of light let us learn different things. Let us learn different bits of information about objects in space. Now microwaves are very useful in looking at space as well, but they're really useful when it comes to learning about what happened a long time ago. So when we look out as far as we can into space, we see what's called the cosmic microwave background radiation. And that's basically the leftover remnants of what happened in the very early universe, not long after the Big Bang, just 380,000 years after the Big Bang. And these are very small fluctuations, very small changes in temperature that we're seeing in the very early universe, at the point when galaxies and stars would be starting to form, or the changes that would have affected how they started to form. We can use infrared light to have a look at the sky. So here I've got the constellation Orion, invisible light on the left and then infrared on the right. Obviously the one on the right is far more colourful, and what that's showing you are all the areas that there could be the potential for new stars to be made, where there's lots of dust and gas and energy that could end up creating new stars and new star systems. And again, if we used a massive telescope to zoom on in the bright regions, we'd find nebula there and stellar nurseries, which are where there are new stars being born right now, as we see it. We can use X-rays to learn about extremely hot objects, which, it could be stars, it could be black holes, it could be things called neutron stars or quasars, which, sounds really cool, but you don't need to know about, so don't worry. And just to give you an idea, here is the Crab Nebula as viewed using 6 different types of light. So you can see all the different things that we can learn about it. I think it's brilliant. And in the end, this uses fairly simple physics for us to be able to learn about these, but also be able to learn about the individual stars themselves. We can learn about stars and what they're made of using physics that, well, you used in 3rd year. By using some physics that you might be even more familiar with than that because you've dealt with it for a long time. And that's by using the fact that we know that white light gets split in to all the different colours when it goes through a prism. Light spectra. And that image in the bottom left I just included because it was cool. It's nothing to do with lightning suddenly hitting a shield of rainbow. That's not how it works. But the idea is that every single colour of light has its own wavelength. Violet's got the shortest, red's got the longest. And what we can do is, if we have a look at all of light, it's got this continuous spectrum. So white light can be split into all these different colours. The full rainbow actually expands beyond all the way into all the invisible types of light that we can't see. But we only need to worry about the ones that we can. And the thing is, all the different elements out there, every element, when you heat it up, it gives off its own special fingerprint that lets us figure it out. So here, you can see white light up the top, that continuous spectrum of colour, but hydrogen now has a couple of blue lines, a red line, that make it quite visible and are quite easy to recognise. Lithium's got a bright orange line, a few blue lines, a few red lines. Carbon's really complex, but these lines are specific to every single element. And because of that, if we look out into space and we see those patterns of lines in a star, we can tell that star's got hydrogen in it. And if the lines are really thick, we know there's lots of hydrogen in it. Or if it's really thin, well, there's not much hydrogen in that star. So we can learn a lot about them by doing this. And actually, this is something which you can be asked about in a test or an exam. So, there's an example on the board here, on the screen, even, where we've got an unknown star up at the top with these patterns in it, and then there's a number of possible elements that could make up that star shown below it. Just in black and white, because that's what you get in the test. So if you have a look at it, which patterns match up? Which elements can you see in that unknown star? Might help to find a ruler and just put them along, but if there's any line missing, it's not there. They all have to line up. The answer is hydrogen and helium. Which is, to be honest, the most likely thing to find in any star. Because most stars are primarily hydrogen turning into helium. However, with that, we have gotten through the entirety of the space section of the course.